Welcome everybody for the afternoon session. Our next speaker is Anton Kapustin from Caltech, and he'll tell us about thermalization and chaos.
Thank you very much for the opportunity to speak at this conference. Celebrate Markus's birthday. So the subject of this talk is very, well, in some sense, very well. It's a second law of dynamics, and it's one of the most fundamental physical principle. You can observe every morning in the kitchen when you break eggs, you don't, and it's very fundamental. From the many formulations, one informal one, I forgot to get to this. Well, I can explain it to a layman. The first law says you cannot win, and the second one says you cannot even break even. So this is a very loose definition. That's what I like, and what I try to discuss is this one. So if you are just sort of generic, in some sense, isolated system, preferred in a well-behaved state, then eventually it reaches the state of maximal entropy. And the maximal entropy state is called the equilibrium state. Now, what exactly? The little what this means depend on the situation. You could have some dynamical law which conserve energy, then you should maximize entropy. That will go with with energy fixed, well, Howard and energy fixed, and then the equilibrium state is then is a Gibbs state. That's a normal situation, but also situations when you don't have conservation of energy, when you have periodic drive. This is also on Floquet systems. So in that case, when you find out the state of maximal entropy, since energy is not conserved, your system can, receive and lose energy through interaction with the drive, then you should just maximize entropy without any constraints. So in that case, state of maximal entropy is basically the infinite temperature state. So it really has all maximal entropy on all states. Now, of course, in many cases, such state doesn't exist, and then if you expect the system never to reach any stationary state, just have to run away, keep temperatures grows and grows under the influence of a drive. But if there is such a state, then expect the state to gradually approach the state of infinite temperature state. That's what the second law says in this situation. Now, second law is a physical principle, but we'd like to deduce it mathematically from the laws of mechanics. And of course, this problem has a long story, it has a long history, and in order to prove anything, first you need to formulate the question more precisely. So in this formulation, I said it's not clear what is generic, first of all, and it's not clear what is a well-behaved initial state. Well, there may be different opinions about that, but it's clear that some codifications are needed. For example, we don't expect conversation to happen, in all situations. If you have a local observables, for example, which are conserved by the dynamics, then the expectation value is not going to change at all. So that's called many-body localization. That, of course, an exception. That's where you think for generic system that doesn't happen, but still, you can pose a condition like that. And second, well, even for generic dynamics, you can expect all states to thermalize. So in classical physics, you have the well-known Poincare-Ricardes theorem, which says that if you start with a state where positions and momenta of all particles are known exactly, then if you wait a really long time, you're going to come back, very close to the original state. So which means you're not going to thermalent, right? You're not going to reach state of maximal temperature. You're going to come back with essentially the same state. Well, of course, it's like in really academic situation. You should never, walk out, know everything in such precision, but still you're going to prove mathematically some state, and you need to exclude some pathological states like that. Okay, so now let's try to write some equation now, which express the second law. So I'm going to use in this talk Heisenberg picture. Instead of thinking about the evolution of state, I'm going to think about the evolution of observables. So that's more convenient. So I have some state, which I'm going to call initial state, like average 0 is initial state. Although, again, can be defined about the initial state when, states don't given at all. So, but anyway, so then this makes discussion in a Heisenberg picture, and A is some observable, some observable function of dynamical observable, which depends on time. And we want to prove that for any observable, we have this state property, that if you take the limit, it's equal to infinity, then you can compute it simply by evaluating the average in this equilibrium state. So for long times, you can just replace averaging over the initial state with averaging over this equilibrium state, the state of maximalization. Now, what are these two things in compose? First of all, the evolution law must be like, what is generic? Well, physicists would say that it's at the very least you need to ensure it's sort of aperiodic, the non-periodic behavior. So that, well, we could discuss later what this means exactly, but you want to make sure that there are no observables which are periodic in time. If they have such an observable, well, non-trivial observable, or so that constant, then definitely you know when that happens. Yes.
This equilibrium state does not depend on A. It's crucial.
Does not depend on
A.
A is the observable you choose it.
Yes, right. So, but the equilibrium state doesn't depend on A.
Yeah, in the equilibrium state, the state of maximal entropy is just state which you just choose. You can compute once and for all without knowing anything about anything. You don't even need to know dynamical law. You just take the system, maximize entropy, find the state of maximal entropy. Hope there is one.
And then you pick whatever observable one thing, one realistic. Yeah.
So a second, to say the initial state, well, again, you can expect it true for all states. You need a nice state. So we'll discuss later what mean. Now, and what is T? Well, T is a time. It typically is continuous, but if you're in Floquet situations or fairly dry, you can just imagine T is discrete. So little. Now, this problem, though I formulated, makes sense both in the classical and quantum setting, and we're going to discuss both the classical and quantum situations. And yes.
How is that what you want to prove different from the ergodic hypothesis?
Yeah, I'll discuss that later. Yeah. So, I'll stick with discrete time for the stuff. It's just the program can be analyzed in this issue. You have some way.
Sorry, yeah, we don't require, do we require finite time or it's time where you can?
Yeah, I'm gonna prove this statement. That's the only thing I'm gonna try and prove. There's no finite time statements at all. Okay. For other simplicities. Okay, so the provisional definition, I'm going to change it a bit later to say, well, it's periodic. It just means that if some observable, which is periodic, then that in that case is the constant observable. So a periodic is non-trivial constant, non-trivial time period observables. All changes the definition slightly. There you go. Now, ergodic hypothesis was mentioned here, and there is in the long history of various conditions on dynamical systems which can ensure this second law. And this one called is ergodicity, which is more about averages over time. But then there's a stronger version, which is reminiscent of what I said, called mixing. So, and this, what I'm trying to prove, is actually closely related to mixing, more to mixing than empiricity, to a stronger addition. So let me then remind what mixing is. So we have some state invariant under dynamics. You can say dynamic is mixing with respect to the state if the time correlator factorizes long time. So that's called mixing property. Now, it doesn't look very similar to what I wrote before, because first of all, it's all relative to some state, okay? And there's only one state involved here. Well, in the statement which I previously wrote down, there are two states here. Okay? There's the initial state and there's a particular state. There's some difference. But there is a connection. I'll discuss it later, but for now, let's just note the following. First of all, this condition, mixing, does imply the big a priori. I'm not going to discuss how they use it. It's not very difficult. Well, okay, there's some condition on the state. Aperiodic is a condition on dynamic, not on the, and mixing is a condition on the state and dynamics. But suppose your state is faithful, meaning has this property, then mixing does imply that dynamic is aperiodic. For it's said that for physicists every continuous function is differentiable, and also similarly for physicists every necessary condition is also sufficient. So periodicity is a necessary condition for mixing, but physicists often say, okay, keep Okay, then all integrals, if nothing is periodic, then probably it's mixing. So that's a typical theory of physics way of thinking. But of course, mathematics are not so unserious. Actually, it's a lot of time trying to prove that for certain parts of the system, being aperiodic does imply mixing for certain states. And that's why it is a kind of stronger version of this ergodicity hypothesis, because mixing sort of strengthens ergodicity. And sometimes it works. So let me discuss it's one example where when it can be shown that's the case. Suppose we have this very simple classical space two-dimensional torus, and with a standard simplex structure, and then consider it with just dynamics given by some canonical transformation, and let's say it's linear, just to make for life easy. So there is two coordinates which are periodic. So you want a linear transformation be compatible with periodicity, this A, B, C, D must be integers. And if you want to be invertible, then the determinant must be 1. Now, when is such a thing aperiodic? That's very easy to find out. It's aperiodic when the eigenvalues are not of this matrix are not roots of units. And it's not very difficult to show that it does imply mixing in respect to this uniforms. Let me illustrate. In fact, I might draw pictures which shows.
That I missed. Where's the condition that it's integer come from? That ABCD?
Oh, because if you shift x and y by 2 pi, you want to show that you want to transformation of torus. X and y are not just real variables; they're periodic. If you want periodicity to be make sense, but transform variables, then you have to impose the thing. So, and not even draw the pictures. So, but let's take this matrix to be 2, 1, 1, 1. So this clearly has determinant 1. And then let's see what happens to some configuration on which periodic take it to be a cat for some reason. So it goes back to our null. So let's see. So this is in original first iteration. Let's just sort of see this cat. Third, fourth, no, this is third iteration was already nothing like cat. It's all been squashed. So somehow in all physics, the cases of cats, cat always, right? So the Schrödinger cat sort of dies. Arnold's cat clearly, maybe too, it's still figure alive, but those alive iterations. Now, how is this mixing related to this thermalization state, which I wanted to prove? Well, they're related. Suppose the system is mixing with respect to the equilibrium state. Then it dynamics thermalizes all states which are not too different from the previous state. So what does it mean? Well, let's look at the classical case, which is easier. In that case, this means the probability matter. Well, for classical situation, average is the integral over your averaging or your phase space with some probability distribution. And this probability distribution, well, there's a uniform one corresponding to the equilibrium state, and then or Gibbs state, and then if your probability measure is a equilibrium one times an integrable function, then you say it's not too different from the equilibrium state. So mathematically, it's almost measure absolutely continuous with respect to some other field. So, okay, so why does it? So now we can actually see why mixing reduces to thermalization. Could actually say so. The average, this initial general state, is equal to the average in the equilibrium state over modified observable, and then you can apply mixing property. But for the equilibrium state, you see that this thing factorizes and becomes simply average in the equilibrium state polar chain. So mixing with respect to the equilibrium state implies thermalizations of every nice state. Right. So that's the flavor. Now, in case of sort of this cat man, you can see explicitly what happens. Suppose I have some observable, which is a function of torus. You can expand the function into a Fourier series. And Fourier momenta are integer here, right? So it's a complex situation. So what happens under evolution? Well, the cat map is very simple. It just maps Fourier component, Fourier component at time n is simply Fourier component at time 0, but the different value of momentum. Just take momentum is multiplied by the transpose of this KXL powered. Okay, so why does it how do we see the difference through thermalizing? Well, if both eigenvalues are not on the unit circle, then one can show that in this limit, this vector, it always diverges. Basically has no choice to diverge. No, of course no, at least it's on zero. So, if you take, to start evolving your function, in Fourier space, all these Fourier components are shifted to infinite momenta. And then you ask me, what happens if you average over any reasonable distribution? Well, there's something called Riemann-Lebesgue lemma, which says that average of something which oscillates very, very fast is essentially zero. Okay? And everything shifts to infinity in this limit. So the only thing left is the constant part. Right? So in the constant part, that all being survives averaging, that actually is a statement of this. So basically, you this limit, averaging over a random sort of nice distribution becomes averaging over uniform distribution. That's all there is to how this all makes in Lewis correlation. Okay, so is there anything else to say? Well, actually, quite a lot, because you see, we're interested in many-body systems, and for many-body systems, mixing does not imply thermalization of all state domains. So this ergodic mixing stuff that actually doesn't prove, even if you can establish the system as mixing, which is still very trivial, that actually is not good enough. So why is that? Well, let's take some very simple situation. Many-body situation, we have just a product of identical compact faces. So you have this Mi, which is of finite dimensional negative, followed by the force, or is here, and then M is the independent product of V. Then typically is a classical spin chain. Okay, and suppose you have a translation invariant product state, like the simplest reasonable state would be just product state. Identical state for every, for every classical spin. And let's have a very simple evolution which just shifts the whole chain by one. So very stupid really evolution law, but what in truth is dynamical system is mixing with respect to such a state. And also more equilibrium state. But this state is actually preserved by the evolution. You start with the product state, you act by this very silly mixing law, but the state stays the same. It doesn't become a uniform state. So there's no thermalization, even though there's mixing with respect to the equilibrium state. Why is that? Well, so what does actually mixing ensure in the many-body case? Well, what it does is show that if you have mixing dynamics, then a local perturbation of the equilibrium state relaxes to the equilibrium state. So you stop local perturbation and look at Pflaum analogy. Pflaum times the low way. Yep.
Hey, but just to have myself oriented with regards to the literature, I remember about 10 years ago, Shivaji Santi was writing these papers on classical and quantum dynamics and the ordinal map and perturbed ordinal map. How does this relate to that? Is it a sort of rigorization of that, or it's just completely separate story?
So this, what I'm saying so far, you can literally like a standard, but I'm just saying it doesn't address the physical question. The physical question is why the states thermalize, even though when they're not locally different from the equilibrium state. Sure, have state which is everywhere different from the equilibrium state. You're gonna thermalize, and mixing doesn't say anything about it. So the point is that this statement, this innocent looking requirement that your probability measure is the equilibrium one tensor function is actually not very innocent in the many-body case, because it means essentially that it actually does imply that your state differs from the equilibrium state only in some locally. If you go far, it just since the equilibrium state. However, we do expect that many, although not all states which are different from equilibrium everywhere, still relax to the equilibrium state. So mixing doesn't tell us anything about that. Okay, so actually, what do we expect of thermalize? Let's discuss that. So let's pretend it's a bit Floquet by the system. So thermalization means heating to infinite temperature in this case. Okay, so definitely, any state which is easy to prepare, you want to thermalize because, we want something reasonable to thermalize. Some weird stuff, we don't care about what it does. Like say with all just a point in a phase space, nobody cares that it doesn't thermalize, so we cannot prepare. Product states are easy to prepare, so that better thermalize. Well, okay, maybe you want to demand the on-site sorbibility density is continuous functions. But other than that, would be pretty much anything. Okay, if you start with the product state and entangle it somehow, but entangling it something correlate neighboring spins, basically.
So sorry. What's the definition of easy to prepare? That's what you mean.
Yeah, but explainable.
Something like a finite depth from the product or something.
Yeah, for example. Yeah, I'm just trying to see which things for sure I want to include in this kind of states I want to show that thermally. So product stage data should be there, arbitrary. Not necessarily translation variant, arbitrary. Thanks. And the short range entangled one, if you're complex, do some classical quantum circuit applied to product state, they should also better thermalize. Because again, so easy to prepare. Gibbs states, okay, you start with a Gibbs state of some nice Hamiltonian. Well, that's easy to prepare because you can make it by bringing it in contact with the thermal path, right? Okay. And then you start applying this draw. You expect that to thermalize as well, to heat up to infinite temperature. So we better include all those. And cannot deduce any of the thermalization of this from mixing, that you can pull mixing. Okay, so now let's specialize to start precisely what I'd like to show which class of system like we try it with to start. Because of course in general it's incredibly hard. So let's try to do something specific. Okay, and I'll do the following. I'll do the system whose phase space, or not, I'll do the classical stuff. So I'll take the system whose phase space is a product of compact phase spaces, some compact manifolds of some fixed dimension. And all identical, the serial identical. And you can call this spin chain if you wish. So a point of such an infinite product is an infinite sequence of points in this MR. By the way, I just they choose one-dimensional. Why is it like one-dimensional array of spins? Why is a spin chain rather than spin system in higher dimensions? Actually, for no good reason, just because it's easier to write formulas. Actually, what I'm going to tell you applies equally well to arbitrary dimensions. Okay, so now I'm going to have the dynamics, which is going to be discrete time. And this just means that I'm going to apply some rule which updates the, which you can know where I am in the system, at which point in M I am, then the rule tells me where I am next moment. Well, let's pick some nice rule, which is first of all translation variant, reversible or invertible. So, and also it's a classical situation, so probably want to show something differentiable. Very important requirements to the local. So to be realistic, the local rule. So meaning that the updated value of xi depends only on this xj's, the j not far from for some fixed radius. And finally, well, so volume preserving. And more realistically, if this phase space, each of them is symplectic, then probably you want to require the update tool, which is a canonical transformation. So if is wanted to be symplectic. Okay, that's still very general, and there is no way to analyze this currently. No tools. But I'll specialize further. But at least in this context, I'm going to specify what I mean by aperiodic. So first of all, I already assumed both discrete spatial and time translations. So I can, shift in space. That's and then will time simply translate this way because my rule is doesn't have a piece of time dependence. So the overall the group structure is z-time. So that's S and T generators of spatial time translations. And when I say that this system is aperiodic, if there are observables which are preserved by some combination of time and spatial translations. That of course, rules out an observable which is periodic, but also I don't want observable which is just shifted after time, some translation. So we can deal with a solid ball. But without playing solid ball. And what I'd like to prove is that if you have such a system, then it thermalizes any well-behaved initial state. And I still have told you what well-behaved initial state is. And it doesn't matter too much, provided it lose all of these states already listed in the previous slides. So aperiodic for me is a replacing of generic. So if the follows condition that this is likely to be imposed, we would like it to be sufficient for formalizations. Okay, in this generality, you cannot really do anything. So let's impose a very strong condition which makes it analysis manageable. let's take this Mi to be a torus. Then it's a commutative group, and then the product is also commutative group, now infinite. And let's require the update rule to preserve the group lot. So this M is just also not just a manifold, infinite manifold. It's a abelian group, and you want the law to be preserved, the additional, the group structure. So in the context, like this Arnold's cat map was like that, right? It was linear in X and Y. Essentially, I want to impose linearity even in the many-body context. So I want this map update rule which maps, this axis to new axis to be linear in order. Okay. So, and just like in the Arval's cat map, I have a matrix which any such rule can be specified by an infinite matrix. Now it's infinite. It has integer entries like this Arval cat's map. It's infinite, but it's not too complicated. It's also the band matrix. So it has non-zero elements only in some neighborhoods of diagonal because of this Floquet condition. And finally, I can state some results. So suppose I have a state which is equilibrium state. It's the uniform probability distribution on my count. It's a very special probability state. It's the maximal entropy states. Then I can show the following. There is some very large path of states. It includes all product states with the uniformly differentiable probability densities, all Gibbs states of nice Hamiltonians, such that any aperiodic algebraic Floquet dynamics thermalize every such state. In this sense, this is true for any continuous function. So in other words, second law holds for all aperiodic algebraic Floquet systems. In this case, a sufficient condition, an astrophysics actually is sufficient. And how does it work? Well, it works in more or less the same way as for Arnold's cat map. Why does it work? So, well, suppose I have the observable. I can expand it again in a Fourier series. And the only difference compared to the cat map is not my Fourier label is infinite itself. It's an infinite number of these integer vectors. Okay, it's infinite, but only a finite number of components is so only a finite number of components is non-zero. All but a finite number of components with zero. So it's an infinite vector bubble. You have zero starting sample. And in Fourier space algebraic this vocabulary is very simple. We just take Fourier component at time n. It's simply Fourier component times 0, but with a different value of this infinite vector. And just multiply q by this infinite vector q by the infinite matrix and get mu. And one can prove that if you have a periodic condition, then this quantity diverges. What is this quantity? Well, you can look at this. If you can keep track of what is the largest of these q's. Okay. Different. This infinite vector has the largest q among them. Turns out that the largest, the size of the largest one diverges along both impedance. Where it is, it changes some unpredictable way, but the largest one always diverges. You have this A pairs. This is very similar to Arnold's cat. So the hard work is to prove it actually that this happens whenever you have this A pairs. It uses some interesting number, some interesting algebra. And I also want to tell you then what is this class of states S? Okay, so if I have a probability distribution on my infinite space M, I can first of all look at conditional probability. So to look at conditional probability that on some site, xi is simply coordinates from my r-dimensional product, and mi at is just state of my system outside this site. So I can do the following. Let me create transform this thing with respect to, this my quantum particular r-dimensional torus, get some function, take its absolute value, and then I maximize it over all configurations outside the site, and then maximize over all ultrasound sites. That gives you just some function, which is just function on a r-dimensional torus. Also, over image variable huge, it just takes values in here. A bunch of r integers. And I'll say that the state satisfies this URL condition if this function decays. So basically, it means that the conditional probability distributions are sufficiently nice in sort of uniform way across the different sites. So this is a set I can prove the result of thermalization, and that state proves all Gibbs states of all nice differentiable Hamiltonians and all product states happen. All like product. Okay, so I'll move on to quantum version of the problem, but regarding questions, maybe it's a good place to. Austin? Yes.
If U is the dual Fourier break, right?
Yeah.
So what does it mean? You take the largest Q and that.
Well, Q is a vector, integer vector. So say it doesn't matter which norm I choose, all equivalents. We just take the largest. If you have r-dimensional integer vector, I can just take the largest absolute value or sum of square Euclidean norm, and it doesn't matter. They're always related.
Question. So your family of initials aids it to the probability distribution, but I guess that is more aware of the local structure of the system.
It's a probability distribution on my infinite phase space.
Right, and there are these opinions that we like Woodstein et al. That when you talk about the second law or something like that, the mixing of probability distributions or the association of probability distributions does not imply that.
Wait, what?
Can you speak on it? Like, when you're talking about the second law and you just consider in like the topologization of probability distributions, that's not strong enough to get to something like the second law.
So if you impose probability distribution,
like if you just impose the probability distributions to analyze, that's not sufficient to get something like a second law. In general, that you also need something like concentration of the observable on free space.
I'm not sure what this means. If I can show that a rotation value of any observable, a product of equilibrium fluctuation value.
In a probability distribution, like not in every individual state, right? Or almost all individual states.
For me, state is the same as probability distribution, just a way to evaluate.
Okay, I'm thinking of like points in phase space.
Oh, yeah, no, I refuse to think about points in phase.
Yeah, so I guess what I'm saying is there are these opinions by Woodstein et al. That tell you that if you don't think about points in phase space, you don't really get to say it as we see it in experiments.
Yeah, well, I think same quantum situation. The only notion or state is sort of probabilistic, is the average.
That would be a next state, not your state. I guess that's so. Yes, it's a pretty
sure. So I mean, like quantum mechanically, the only sensible notion of a state is statistical. So that's in behavior. Classically, you can contemplate point-like states, but this is like a completely unrealistic. You can do it, but you cannot like ever create such thing in a lab. So statistical state is a more reasonable notion also in the classical.
Yeah, but in quantum mechanics, there's a difference between mixed states and pure states.
Not important but here, because I want to prove a relation both for pure and mixed state.
So if you get to pure states, then I think I would have an objection to that.
Yeah, I don't know this stuff pure states as well. So doesn't classically your states are bad. Quantum mechanically I'd want to yes. All right, so let me discuss now the quantum version of this problem. So first of all, in the case of an R-node scat map, can actually quantize it in a natural way, but the resulting dynamical system is not mixed for trivial reasons. Because when you quantize a finite compact phase space, also get a finite dimensional Hilbert space. And then the finite dimensional Hilbert space can never have thermalization because evolution is quasi-periodic. We can actually make very complete in this case. Well, basically, we quantize this torus by making x into operators. Okay, so we can have operators. But anyway, then write this formula. like have a compliance constant which is to phi over some integer, and eigenvalues and quantized. So basically your x and y becomes sort of pixelated, right? They take discrete values. And well, of course, this is all n-waving big. The better way to do this introduces 2 pi operators, which is 2 pi I x hat and 2 pi I y hat. Those are better defined. Well, you reach same conclusion. They satisfy this condition, therefore you only have n eigenvalues. And now update rule. Well, it's again 2 matrix, L hat, but now it's it's only need to be defined by modulo n, integers modulo n. And for the periodic simply follows from the fact that any such matrix raises some power 1. And actually, well, for example, if you look at, say, they take in the n equals 10, take the same guys before, but now think what is integers modulo 10. Then if you raise to the 30th power, get 1. And here's like what happens with this cat. So I put the same cat but pixelated, and if I iterate it, it's kind of all scrambled, right? But if you continue iterating, it comes back. Now, actually, in reality, if you actually try to do like the previous pictures, also had some pixelation, right? It wasn't visible, but it had like maybe like 200 pixels. So if I repeat it for a while, even even though it's a classical map, because we use computers which pixelate everything, it actually would come back if I iterate it a lot more times, right? So this thermalization really appears if in strict classical limit range actually cannot resolve any points. Can you have absently can have arbitrary resolution. Finite resolution essentially in the quantum situation though, so nothing, everything is specific others. Okay, so now to talk about thermalization, in one case we need to look at many-body case. You need a many-body Arnold sketch. That is, you need to look at this quantize this Floquet spin chains. So a quantum Floquet spin chain is just an infinite one-dimensional system of qubits with a revolution given by discrete time, translation invariant, unitary evolution. And that's like quantization, what I before called classical Floquet spin chain. So quantum mechanically, another term is quantum cellular automata. So quantum, from the mathematical viewpoint, you have some algebra observable to the noncommutative, and you have a map from this algebra to itself, which is invertible and preserves algebraic relations called the star automorphism. And we'll commute the spatial translation also. And as before, we say that this evolution is aperiodic, it has no solitons. So there are no local observables which are preserved by some power of alpha up to translations. So that's inductor. Okay, now we have a question. Does such a PCA, which is aperiodic, does it thermalize all wave behavior quantum states? And by well behaved, that again means at least all the states are listed, but now in the quantum set. So that turned out to be a much harder question too. I cannot completely answer it for all the states I care about. But let us say what can be done. Okay, first of all, again, like in the classical case, unless I do something, specialize a little bit my update rule, my quantum solitondom, I cannot say anything at all. So in the classical case, we use this algebraic, what is this, and the quantum version of that is also the Clifford quantum solitondom. So, and make discussion simpler, to just specialize to qubits. So in principle, it works for arbitrary number for qubits, right? So it's a d-dimensional Hilbert space, but just look at two-dimensional Hilbert space on each side. So a Clifford UCA maps a Pauli matrix on some site to a monomial Pauli matrices on sites in some neighborhood. It's called Clifford QCA. Now, for general QCA, it would map a linear combination of such things, and it's very difficult to say anything about thermalization that kind. But for Clifford one, it's mandatory. And this similarity with the classical case, a Clifford QCA can be parameterized by an infinite band matrix with entries in 0 and 1, or integers 1 to 2. You can think of this as a quantization of the classical algebraic because you could just take the the update rule in the classical case and reduce modulo 2. And that's going to be a valid update rule per quantum system. I could have done also reduce modulo n, and then we get as n increases, it'll be more and more classical, but still will be quantum. So somehow, if you work instead of in modulo you work with integers, you're classical, but in this algebraic context. But if you work with integers modulo n, you're quantum. Okay, now we have a more manual question. Does an aperiodic Clifford, you see, thermalize well-behaved quantum states? And this question was actually asked essentially by in 2008 by these 3 authors in the case where they had a single qubit per set. Okay, they didn't really ask this exactly the same question, but they looked at the case when the initial state is a product state. And here's a theorem they proved. So we'll have translation invariant product state. That's very, very special. It's not, for me, it's too special. I don't want product states only. And translation invariance also should be for. So anyway, but that's what they assume. And you have a aperiodic Clifford QCA with a single qubit per second. They use some other terminology, not aperiodic. They call them fractal. But it means the same. So then they prove this theory that then you have thermalization statement. Now we're going to generalize a little bit. One can so this implies also that you can generalize a little bit. If you replace product state with a state of this form, sort of entangle your product state with some Clifford vector, you still have the same culprit. That's kind of trivially false or mistake, and they don't exist. Okay, so that's good. Maybe we should try generalizing this result. But before we generalize it, turns out that the theorem is wrong. There's a gap in the proof. So, one can patch it up, but the result is not exactly what we claim. So to patch it up, you need to use, one can map Clifford. The whole, the proof of this theorem, this paper is based on the correspondence between Clifford QCAs and classical cell automata. So Clifford QCAs are quantum cell automata, which are essentially equivalent to classical ones. So lots of results from literature on cell automata can be, imported to theory of quantum cell automata. Why this first one is? Well, turns out, so they sort of did it by hand, but turned out there's an error in the proof. But there's a theorem by there's a result by these authors with one few cell automata, which allows you to prove the polis. First of all, let me here's the definition. We say that J to the subset of natural numbers, it's called density 1 subset. If these are contains almost all interviews in the following sense. If you ask which fractions is contained in the intersection, look at the first n integers, and that's which part is in J. The fraction approaches 1, then most. For example, all composite numbers have density 1. All numbers which are not complete squares have density 1. So conversely, the complement of density 1 for density 0. So density 1 means almost all. And one can deduce from this result the following quantum result. You have an aperiodic Clifford QCA acting on a system with a single qubit first site. Then this result holds for all product states, translated random product states, not for all times, but for almost all times. You need to give to some exceptional zero density subset, and then converges for all. But the subset is different between the burrows. Now, if you experimented, of course, it wouldn't make much of a difference because you are vanishing a small proportion of times is invisible. But you'll see that expectation values generally approaches the expected one, but then suddenly at some exceptional values it just jumps. If you average over times, like you in the ergodicity here, then you will have strict convergence. But this is only important if you look at each time individual. Your average over time, which will say. Now, this can be generalized to much more general states. Let me describe a couple of the direction. Same paper. First of all, let's take just probably set just not translation invariant, but sort of generic in the following sense that if you look at Pauli matrices, take a look at monomials of Pauli matrices. Expectation value of any monomial in Pauli matrices cannot be, in absolute value cannot be greater than 1. And suppose it's strictly less than 1, and moreover there's some constant strictly less than 1, so it's true the for any Pauli monomial that bound them all. Okay? Then such states are also thermalized for almost all times in the same sense. So second law applies for almost all times. Okay, here's another result. Suppose you still have a state which is shortly entangled, meaning you start with the product states and entangled with some 2C, not necessarily Clifford or just some awake agent. And suppose this state is sufficiently close to equilibrium state in this sense. Okay. How false should it be? Well, that depends on this choice of this entangler. Now I can show that all such states are also thermalized by periodically per QCs. That's not very difficult at all. So why is this different between quantum and classical thermalization? Well, in the classical case, thermalization has to do with this blow up of this Fourier momenta. But in the classical case, in the quantum case, you have your Fourier momenta around not on integers, but integers modulo n. So where n is fixed, it's your QD whatever, over its space dimension. There's no way this cannot blow out. So instead, you have operator spreading. Thermalization is due to operator spreading. Then the side of support of the local observables diverges. Okay. However, if you ask how fast does it diverge? Well, you can prove that it diverges for almost all times, but not for all times. So that's the problem. It spreads, but sometimes the size jumps down. Okay. Okay. So here's an actual numerical experiment with some particular cellular topological. See, at first, it's now observable, which has size 0, this single set observable. It starts growing, sort of linearly, but it fluctuates a lot. And then suddenly, starting here, it sort of doesn't grow at all. It just fluctuates around the same value, right? Like if you continue, it can actually do this much for a very long time. So I can tell you, we did it for 100,000 and like up to 100,000. So, okay, it does start to grow very slowly. It looks like it grows at the best logarithmically. Okay? In fact, we can't even prove that it grows because, as I said, only can prove it diverges. You can exclude some exceptional values. Okay, maybe you don't need to see these exceptional values, but this and this on this plot, you see that some values where the thing doesn't drop down, but it still sort of continues to grow big. But we don't know how to prove that. Nobody knows now. So anyway, this is very slow operator spreading. And I'm going to show that it happens for almost all time, and that's what thermalization relies on. So it's much more subtle property in the quantum case. And because of that, we also don't know how to prove the second law for all the states of interest. For example, take a Gibbs state of this quantum spin chain. Does it heat up to infinite temperature if you wave long? We don't know how to prove that, unlike in the classical case, because so operator spreading doesn't seem enough to that. Okay, so let me summarize the talk. So first of all, for Floquet systems, thermalization just means heating to infinite temperature. The observation I'd like to stress again that mixing, which is in strong ergodicity, is still not strong enough for thermalization of most interesting states. So we need to work harder. Even if you prove mixing, that doesn't really prove much. But for classical algebraic Floquet system, one can prove that second law does hold for a very large class of initial states, precisely where emphasis would expect to apply. For quantum systems, of this conversation of the systems, well, first of all, since one needs to relax to simulation from almost all times, and second, we don't only prove the simulation for very fairly narrow class of states. But experimental, if you do like numerical experiments, it seems like formulation holds even for states for which we do not know how to prove that they actually thermalize. So there's something happening which we can understand. so on. And well, the other thing, just I guess it's well known, but still like emphasize. So quantum thermalization has a different mechanism. It has its way to operate a spreading in physical space. That's much more difficult to control. And again, so I talked about classical spin chains as one-dimensional system, but actually nothing here depends on dimensionality. It can be done for arbitrary dimensional space. Thank you.
We have time for some questions? Please.
Your quantum theorem, which holds density 1, sounds a little bit like quantum ergodicity, which holds for density 1 subsets of like. Is it just the case then, or another per analogies?
So I don't know, but this does imply ergodicity in the usual ergodicity, but so in the quantum ergodicity it follows from this thing. It's stronger than quantum ergodicity. If you average over time, you do get that. If you average over some time n and take n to infinity, then you do get convergence in the usual sense, because the zero just this pure average over time.
Mike?
In the classical case, is it possible populating that you have like a kind of probabilistic cellular automata?
Well, classical theory is not closely related to classical cell automata. The quantum theory relates to classical cell automata.
So in the classical theory, like a time evolution was like at each time step you do some kind of canonical transformation.
Yes.
But can I like have like 3 different canonical transformations?
No, you can certainly do. Yeah, you can do yes, or a probabilistic evolution. It would correspond, I guess, to an open classical system. I was interested in isolated systems critically. I suppose it's much easier to formalize it. You add some randomness.
Please, right there.
So you say you can prove thermalization for short range and double states that are close to the equilibrium state.
Yep.
What does close this mean?
It just means in the usual states, they form some Banach space, and this is what poses in this school in this Banach form there.
Okay. In terms of big quantum information measures or something, is this got some distance between necessity operators?
Yeah.
Other questions? Please.
For Floquet systems, isn't it more natural to also include the dissipation?
Oh yeah, no, I don't. Well, think about systems which are just don't exchange energy, or there's no like unpredictable stuff. We just have like periodic drive, and that's it, mechanical drive, right? So if you allow some band to be present, right, then of course totally different situation. So there's no mystery about thermalization. It's gonna happen simply because it was information because of the exchange of direction with the band.
Other questions? Yeah, please.
So also your measure of thermalization is it related to this preenness nor you get like kind of circular considering the
Merging yes. What is it's a particular counterclockwise structure correlate of many bodies, is it?
I'm not trying to listen.
Raul has a question.
So, 10 years ago, Shivaji-Sondhi was writing papers on operator spreading and thermalization and quantum maps, including Arnold map from the torps. Do you know these old papers?
No, I don't. But thanks for letting me know. I'll definitely check them out.
Okay, maybe on that note, we thank Anton again